In this video, we're going to compare and contrast the challenge of identifying global extrema under two different conditions. The first condition is on a closed interval and with, this is important, a continuous function. If you imagine sketching on some interval a continuous function, whatever it does, you can see quite quickly that there will be a point that is lowest and there will be a point that is highest. There's no way for this function to escape if it's going to be continuous. So if we put barriers of a closed interval, which means including the endpoints, then we're going to find a highest point on that interval and a lowest point, guaranteed. Even better, we can guarantee that those global max and mins will occur at either a critical point, say like this point here, or where we ended up cutting off the interval at some endpoint of the interval. And the process is straightforward. To find out where your global max and min are, you find all the critical points. So in this case here, we would identify the critical points here, here, and here. We would find the endpoints. Those are built into the interval. And then literally would say, how high is that? 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 The point that is the highest is literally the highest. It'll be the global maximum. Comparing all those points and finding the single lowest point gives us the global minimum. We really like looking for global extrema on closed intervals because there is this nice clean process for it. In contrast, when we have an open interval, all bets are off pretty much. So if we have some interval that does not include the endpoints, then it may be that the function has an asymptote. It might even be continuous on that interval, but it might have an asymptote that shoots off towards negative infinity or positive infinity. And so that means we have no guarantees whatsoever whether a global maxima or minima will exist. The best you'll be able to do, say in this case here, is show that this has a global maxima, and you can get a convincing argument by talking about the single critical point. Okay, there's only one critical point, and everywhere to the left the slope is going down. Everywhere on this side the slope is going down. The function's going down. And so the only place that can be the highest would be the critical point left over. These arguments tend to be more complicated. They are actually mini proofs. So just be aware of that when you're asked about global extrema on open intervals. You have to have some convincing argument for why the point you're looking at is higher than any other point on the domain. And this unfortunately includes the usual domain for most of our functions, negative infinity to infinity. That is by definition an open interval because we can go all the way out, but there's no endpoint on the intervals. As an example, take a look at this function here and think for a moment whether it has a global maximum or not. Pause the video and then we'll come back and check in. All right, there's two possible ways to answer this. One is that we have seen this before, and so we actually know what the graph of this is. We know this is a graph that has two critical points and is a cubic, and so it's shaped like this. And so we know the graph goes off towards positive infinity, so cannot have a global maximum, and we would be done. There's another alternative for this though, which is if we're trying to show that a function does not have a global maximum, we could also say, hey, what happens to this function as x goes towards positive or negative infinity? Well, as x goes towards positive infinity, the biggest term in this sequence here is the 2x cubed. All the other powers are lower. So this is going to be the term that dominates. And so when x gets bigger and bigger and bigger, we cube it, it gets huge, and it stays positive. This function is going towards positive infinity. We actually have that captured in the graph here. And as soon as we see that, then that means that there can be no global maximum. If the function keeps getting larger and larger and larger, then there's no single highest point. And we're done. So this is how a sketch or a limit calculation can assist us in determining just whether a function might or might not have a global maximum. Let's consider the same function again, but asking whether it has a local minimum. Take a moment to look at the two options, and then we'll check in. All right. I think based on the last example, hopefully, you answered this quickly to no. Because again, we had that sketch. The important side this time is that when the function keeps going down and down and down, there's no single lowest point. Or we could make the statement that as x gets larger but negative, as x approaches negative infinity, the 2x cubed term again is going to be the most dominant term. When x is large, the x squareds and x's don't matter as much. And if we put a negative large number in here, this function is going to approach negative infinity, and so we have no single lowest point in the end. And if we don't have a single lowest point, that means we have no global minimum. Let's consider another example. X minus 2 to the power of 4, does it have a global maximum? Again, feel free to pause the video when you think about that, and we'll check in. All right, global maximum. Again, we look at the function and recognize, either again through a sketch, that this is x to the 4, but shifted to the right by 2. So it's going to look something like this. And as soon as we see that, we see this function is going off towards infinity as x gets larger. So g of x heads towards infinity. So there's no single highest point. And if that's the case, there is no global maximum. Taking the same function again, what about a global minimum? Think about that for a moment, and then we'll go through the logic. This one is a bit trickier. We do have an open domain, so a sketch would be the most convincing. We know what the shape of this graph is, and so we can see that there is one critical point down here at the bottom, and so it will have a global minimum at that location. This would definitely need a full critical point analysis to really back this up. And to make the argument convincing. But a sketch here would be enough if you added some words and said, well, this is a transform version of the x to the 4 graph. It looks like so. And with that shape, there's only a single critical point at the bottom. It has to be the global minimum for this function here. But because the domain is open, it does require an argument or a sketch with an argument to really make this a convincing statement.